Welcome back. We're now going to continue on with our treatment of forces on an inclined plane, but this time we're going to add friction. So we've already done a worksheet which works out all these forces. We know that we now resolve the weight force into its two components, which is mg cos theta, and this one down the plane here, which becomes mg sine theta. If, like in this diagram here, if we have this object here in the center in static equilibrium, that means that we know that the friction that is going up the plane must equal mg sine theta acting down the plane. To remind ourselves about friction, there are two different types of friction. There is static friction, and static friction, which is Fs, is mu s, which is the coefficient of static friction multiplied by the normal force. The other type of friction is kinetic friction, also called dynamic friction, which is F with a K, and that would be mu K and M, where this mu is a different value from this one over here. That's the coefficient of kinetic friction, and this is a smaller value. So mu K is normally less than mu S because this is because of the less amount of interactions between two surfaces which are sliding over top of each other rather than two surfaces which are static to each other. Excuse me. Right. So if we are looking at all of the forces that are on an object like this, we'll just take the static idea here. So the static, equilibrium is a static equilibrium. Then we know that friction, static friction, which is up the thing, is equal to mu s times n. It also must be, this value here must be equal to mg sine theta going down the plane because it's not moving. So these two are equal and opposite. And therefore, we get mu s n equals mg sine theta. Right, now we know that. Don't forget also that n is, so I've got mu s, and n is actually mg cos theta. Okay, because these two things are equal there. And that means it's mg sine theta. Noticing that mg's on both sides will cancel. So the static frictional coefficient would equal sine theta over cos theta, which we see as mu s would equal tan theta. So the tan of this angle is equal to the coefficient of static friction, which is a great thing to remember. Now, remembering that what is this angle theta compared to this mu s? This mu s that we are going to use, that's the coefficient of static friction, is the largest value that we can make this plane incline at before it starts to move. Okay. All right, let's go and have a look at a few examples. So a 1.5 kilogram block is stationary on an inclined plane, and it's at an angle of 35 to the horizontal. Okay? What's the frictional force acting on the block? So here's our block. There's a frictional force acting up there. It's not moving, so we know that it must be balancing a force which is going down, and that would be F going down. We know that the F down is mg sine theta. So frictional, and it's a static friction, must equal mg sine theta. So doing this, we get 1.5 times 9.8 times the angle, which is 35. So it's sine 35. Okay. Popping that into our calculator now. We get 1.5 times 9.8 times sine of 35. And the answer is 8.4 newtons down. So this is an 8.4 Newton down. Therefore, it's 8.4 newtons up because this block is not moving. The normal force on there is the same as always, and that must be mg cos theta, which we know is 1.5 times 9.8 times cos of 35. And I'm not going to evaluate that because that does not change from what we already know how to do. Right, let's move to another. A 2 kilogram block here is also on an inclined plane. So let's just put an inclined plane there. Let's give it a purple inclined plane. Okay, and the coefficient of static friction in this case here is 0.616. Okay. Right, the incline is moved up slowly and slowly and slowly. It's increased until it starts to move. We know that this angle here, the moment that this thing starts to move down, that angle, the tan of that angle would equal μs. Okay, so let's just go through that one more time. When it is flat, okay, it's sitting on that plane. We now raise the plane, increasing this angle theta. Now, μs is defined as, from our calculations a few moments ago, that it's the angle, the tan of the angle that it first begins to slip. So we can just simply say that tan theta here must equal 0.16, and therefore shift tan of that angle, 0.16, gives us 9.1 degrees. Okay, moving on. A car on the road of a steep hill, so let's give ourselves a steep hill, okay. Rightio, is moving, sliding down at a constant velocity. Now, that word constant velocity is quite important here because it's going to tell us that there is no net force on this, this object. So here's our object, here is our car, and it's sliding down this one here. There is a frictional force up here, and that one is down. Okay. Now, because this is moving, then since this has got a velocity going down, we're no longer using static friction, we're using kinetic friction. Okay. So which we've been given a coefficient of kinetic friction here is 0.4. So we want to find the angle of the road. Okay, so let's just remind ourselves what we're doing here. That F down is mg sine theta, so F down equals mg sine theta. Fk is mu k times n, and we know that that is mu k, that's also mg sine theta. And because it's a constant velocity, we know that these two things must be equal. Therefore, mg sine theta equals mu k mg. Oops, I've got a sine. That should be a sine. That should be a cos there. Cos theta. Okay, apologies for that. So please make sure you change the notes from that to that, please. Cancelling the mg's on both sides, then mu k must equal sine theta on cos theta. Once again, it's the tan theta. So mu k, in this case, is tan the minus 1, theta is tan the minus 1 of 0.4. Let's do that. Shift tan of 0.4. That's 22 degrees. Okay. You can now continue on with the lesson. There is a link to a worksheet that you are going to do, and I'll be preparing some videos to help you through that. Okay.